Good morning and welcome once again to the Hamilton-Jacobi equations. So we will be deriving we will be giving two more lectures in Hamilton-Jacobi equations. So we will not be able to prove every theorem, but we will state some of the important theorems, and some of the proofs are given here, and those who are interested can study that theorem. Okay. So let me recall what we were doing yesterday. Yesterday we are having a minimization, general minimization problem, and then if W bar is an optimal, so you have a functional given by a Lagrangian L, the JW, and W bar is the optimal or a minimal solution, then W bar satisfies the second order ODE, a system of n second order ODEs give what is called the Euler equations, Euler-Lagrange equations, which is a system of n equations. Then we are given specifically three examples. One example is the familiar classic problem from a classical mechanics, where you have your LXQ is the least action principle, follows the least action principle minimization, and L is nothing but the difference in kinetic and potential energy, and which is nothing but the motion of particle under the influence of a force. And what we have discussed here is that Euler-Lagrange equations is nothing but the Newton's second law of motion, given by W prime double prime is equal to F of W bar, that is d phi of W, where phi is the potential. Then we have the Brachistochrone problem, where discussed how do you travel under the influence of a gravity, and what is the minimum path which takes the least time to reach from a point to another point down along a vertical line. And we have seen the corresponding here you use the conservation of energy, and we have defined the L is given by this functional, and then the exercise left out to us to write down the thing, and then you solve it. When you solve it, you see that the solution is actually a cycloid. The third problem we have discussed were catenary, where you have a freely hanging chain, and then you want to find out the shape of that curve, and then you turned out to be it's a hyperbolic function, and there also the minimizing functional is potential energy, and the potential energy functional is written there, and you want to minimize it. We did not write down the Euler-Lagrange equations, left it as an exercise, and then we will explain that while solving you get the solution. The curve is nothing but cos hyperbolic. So what we are going to do today, we are converting that 2x2 system into what is called a 2n first order systems, and which is called the Hamiltonian. So going to slowly introduce now Hamiltonian and Hamilton's ODE. So there is a big solvability issue. I will discuss it here. So let me introduce first a term, what is called a generalized momentum. I will shortly tell you why we call it a generalized momentum vector. Where PS is equal to, I use the standard notation like in classical mechanics, it is nothing but dq of L at optimal solution. W bar is your optimal solution. Okay, so we are again assuming all that W bar of prime of S. This is your generalized momentum vector. Why it is called a generalized momentum vector? Because in classical mechanics, what is your LXQ? LXQ is equal to the kinetic energy minus the potential. This is potential energy. So what is your dq of L here? dq of L is nothing but m into q. So dq at L evaluated, I told you that q is nothing but represents a velocity. So your PS is in this case mass into Q is W bar of S. At that point, mass into Q, that is equal to mass into W bar of S. So you see that this mass into velocity, this is the velocity, mass into, no, this is mass into W, Q is equal to W prime, okay, W prime. So this is velocity, and hence this is the momentum vector in classical mechanics. So what we have introduced is a momentum vector. Okay, so you have your momentum vector. So one of the issue is that, so if you understand the classical mechanics well, so description in classical mechanics, description using velocity, no, position and velocity, that is W prime, that's nothing but your Qs, is the Lagrangian formulation, Lagrangian formalism. These are all typical Lagrangian formalism. On the other hand, description using the position, this is position, and momentum is your Hamiltonian formalism. These are well known in classical mechanics. Formalism. And you can go, so if you given W and W bar, W and W bar, W bar prime, given this, you can compute your position is already there and P, and conversely W, the other formalism, suppose W bar and P is given, then you can have W bar is there and you can solve this equation. You see, you can solve this equation, and given P you can compute W bar. So you can solve it here, W bar prime. You see, that is equal to nothing but 1 over m into, you see, 1 over m into Ps. That's the thing. But in general, so given in general L, if you take it, given W bar and W prime, this gives W bar P, because P is defined like that. So you see, you have defined like this, P. But conversely, converse part is not generally true. Conversely, W bar and P given, one need to solve this equation. You see, need to, because your P is defined like this, need to solve this equation. P of S is equal to dq of W of S, W prime of S, need to solve to get W bar prime. You see, to get W bar prime. So in general, so let me use the other pen. In general, solvability may not be true, because it's an algebraic solvability, and you know that an algebraic equation you cannot solve. This is a nonlinear equation in general, and the other one happened to be linear, and you have a very precise in general solvability need not be true. This is a major hurdle. This is a major hurdle in general. Okay, so we make an assumption we make an assumption now. So we are making an assumption immediately that P equal to dq of xq, dq of L xq can be uniquely solved, for q, and q will be qxp. So q is a solution to this equation, and you are defining your Hamiltonian now. You will see that one definition. You can define h. Now you are defining, so for h I use the variable p. Again it is from Rn cross Rn to R by hxp is defined to be, you will see later more motivation why I am defining this way. P into qxp, see q is the solution to that, minus L of x qxp. This is my Hamiltonian for this equation. So you see, so you have your Hamiltonian equation defined like that. And in classical mechanics, that's where the motivation came. hxb will become, will become mod p square in terms of p by m plus you get your Px. This is same as kinetic energy. This is the total energy now. So L was the difference in energy for the least action principle. So H you get happen to be the total energy. So you define Hamiltonian like that. So you have your assembled theorem. The proof is not difficult. So I may or may not give. So assume let W bar be the optimal solution. Okay, and H as above. Assume solvability, and H as above. Then it satisfies the W bar prime of S is equal to dp of H W bar prime, and this is a system, n equations here, and then you are on P you are writing the system. So this is a system in W and P. The earlier one was W, the Euler-Lagrange equations for W and W prime. It's a velocity equation, and this will be minus dx of H and W bar prime. Further, S going to this Hamiltonian, H going to H of W bar and W bar prime of S. So A is constant. That means that Hamiltonian is constant along optimal trajectories. Okay, is constant. That is Hamiltonian is constant along optimal trajectory. Hamiltonian is constant along optimal trajectories. And if you recall in the introduction, when I introduced the Hamilton-Jacobi equations in the corresponding characteristic curve, these are kind of characteristic curves which you have it. So the characteristic curves, along the characteristic curves, Right now you don't have the Hamilton-Jacobi equation. We only introduced the Hamiltonian, but along the solution, if you really recall at the end of it, you can see if you have the Hamilton-Jacobi equation and the corresponding characteristic equation is along. Are the characteristic equation, that's nothing but your Hamilton ODE. In classical mechanics, S is the total energy, and what it shows that along the characteristic curves, and H is the total energy. The total energy is constant. In other words, the characteristic curves are nothing but the constant energy curves. So to have that kind of interpretations when you finally end up with your Hamiltonian. Okay, so the proof is not that difficult, so maybe I will give a quick proof, but I want to do something more here today. The proof is fine because by definition, if you look at it, Q is nothing but Q, you solve this, right? Q is obtained by solving this P of S. But then this is obtained by nothing but by definition of this one, this is nothing but W prime of S. So Q is obtained by solving. But then if you look at here, the way P is defined, P is this one, TQ of L of X of S, Q of S. And that's how you solve this P. So Q is solved that one, but then your P is introduced like that, right? If you go back here, so you see, yeah, P is introduced like that. So on the part of Q, if you look at it, you have this, you see. So this is what you are solving. So the Q is nothing, this is the equation you are solving. So the Q is nothing but W prime of S. Okay. So you can see that one. Once you have that, that implies, okay, that implies H of W bar, PS, you always write W bar of S, PS is nothing but by definition P of S, W bar prime of S. That is how that it is defined. Q, this is Q minus L of W bar. Of course, S is there all the time, so I will not be writing S and again. So if you define this one, so you will have this definition. So therefore, P prime of S is equal to, so this immediately gives you B prime of S, d by ds of, by definition, okay, dq, P is that one, dq of W bar prime. You see, that's there. But then from the Euler-Lagrange equations, this is nothing but dx. So you see, you already have your Euler-Lagrange equation, W bar prime of S. And that is nothing but your minus dx of, by definition, from here. If you take your h here, so if you differentiate with respect to the first variable, this is nothing but dx of L. So you see, if the previous equation tells you this is nothing but dx of h, W prime and P of S. So you have W prime and you have your P of S. And that's what you want to prove it. One equation, P prime of S is equal to dx of W bar P of S is equal to that one. So you will have that. Okay. Yeah, so you have that one. Dx of L is nothing but that equation. So, okay. And we can also prove that if you compute your dH by dPi, if you compute your dH by dPi, you can easily show that di prime of S. And exercise, you can check this exercise. So I have done little bit quickly, but go through our book. Okay, for any error, W bar of S, P of S. Okay, P of S. You can show that this is an exercise. So that S going to H of W bar of S, P of S is constant. Okay, is constant. Okay, so you have that equation. Okay, so now we want to discuss something else, what we call it a Legendre transformation. So this is what the Hamilton's ODE, which is a system of 2n equations, and then we want to introduce in general case what is this Legendre transformation. Legendre transformation. Yeah, these are all some advanced topics, so it is important that you study properly. You go through it very carefully on the Legendre transformations. Okay, so look at the way, so you have your LP as a, so you are considering L as a function of, so in this case, so we are considering L is only as a function of Rn to Rn. So that we use the parameter P, okay, with the P in Rn. Okay, now look at this, the way the P is defined here. So P is given P, you solve this equation. So look at this one. This solving, you get it. Solving, you get it, Q is equal to QXP. Look at this equation. So if you look at it, this equation, you are solving this one. This equation is the derivative with respect to Q, of course, with respect to Q of some f of Q is equal to P dot of Q minus L of Q, L of XQ. That's the observation. This is observation. So that implies Q is a critical point of this one. P is equal to is the derivative. So you have P minus dQ of L is equal to 0. That means you are looking at the critical. So we are looking at the critical point of F. That is F prime of Q is equal to 0. That's what your exact solvability. So naturally, when you have P is equal to dQ of L is the critical point of F, and then you are actually F is maximizing or minimizing. So you can see that it is exactly maximizing. So this motivates us to define the definition. So you define as a definition Legendre transformation. Legendre transformation. So if you are precisely, you are solving, so given P XP, so if you look at it, given XP, you solve for Q, which depends on P. Of course, you can depend on X, that's fine, because now we are not having this explicit expression. So you don't need X here. Q is equal to QP and H is equal to is precisely the maximizer. So when you define H of Q, you are basically define P into Q of P minus L of X Q of P. So if you really look at it, actually what we are doing is that in the previous case, this equation P equal to dQ of L is the critical point of F of Q, and H is the nothing but the maximum value. So this is a maximizer. It maximizes at Q equal to Q of P, and HQ is the maximizer of this one. That is how we have previously done, and this is exactly motivating to define what is a Legendre transformation, which we will quickly define now. Okay. So let me do this one. Okay. So L as above. So of course we are assuming L as above. Then define L star, which is a dual, but it's a Rn to Rn only, L star. Later you will see soon that Rn, L star is nothing but H. L star, I can always define this one, L star, so I will use the dual variable only. L star of Q is equal to supremum over P of P dot of Q, these are all vectors, minus L of P. This is what you want to understand, the supremum. So if L satisfies the conditions, you see, if L satisfies the coercivity, if L is coercive and continuous and all that properties, convexity, etc. So you have this property of L, and this is a bigger growth, then this is a linear growth. Once Q is fixed for P, this is a linear growth. So basically this goes to infinity, minus infinity, this term, and supremum exists as a finite quantity. So that is where, so with these assumptions, so I can leave it as an exercise for you. There exists P, some P star such that L star of Q, yeah, there exists a not P, okay, this is attained. Your P star of course depends on Q, okay, so there exists a L star of Q. You can easily show that there will be P, yeah, given Q star of P minus L of P. So you see, so you have that one. So you can, so you, the supremum is attained at some P star, not Q star, sorry. So let me, okay, so it is attained for any Q. This is attained some P star of Q. So this is attained. So P star Q minus LP star. You see, so you get always such a P star. Okay, so that you can do it. So what I'm trying to do is that you have L star Q or P. Yeah, sorry, I made a mistake here. Because I used the, for L I am using the dual variable. So let me use this one, P variable here. So and this is the Q variable here. So for L we are using Q. So it's the same thing, but I want to use the variable. So in this case, I use Q star. So given P, there exists Q star of P, and your L star of P is here. You have to use P here, and then, okay. So you have a Q here. So L star of P equal to P dot Q star, which depends on P minus L Q star. Okay, so that's what you have to prove. There exists. That is because of the coercivity and other property. So you will have all these things immediately. This is nothing but your F Q star at P. You see, so you have that theorem. So you can prove immediately like that. So immediately it tells you that. So you are so by definition, you know that by definition, because since this is a maximizing point, so that immediately think that because this is Q star is a maximizer, so that implies your dq of F evaluated at Q star of P is equal to 0. So that is exactly tells you that. So that's a maximizer. Q star is a maximizer to this one. So this has to be 0. That implies P minus dq of LQ star is equal to 0. You see, you have that. So by definition, your H of P is nothing but PQ star minus LQ star, and that's nothing but your FQ star, and FQ star is nothing but L star of P. So you see, so that implies your Legendre transformation H of P is equal to L star of P, the Legendre transformation. Legendre transformation. That's what you are. What I am having is that you actually have the converse is also true. So let me state the theorem here. Converse is also true. Okay. So maybe I will try to state the theorem and try to give a quick proof of it. Theorem. This is called the convex duality between L and H. Between L and H. Assume L as above. That means L is convex, continuous, and cohesive as above. And okay, and satisfying all assumptions, and H is defined as, and as above, assume solubility. This is important. So you are assuming solubility and define your Hamiltonian H as, so H P is equal, which we exactly define, and the solution P dot of QP. QP is the solution corresponding to P minus L of QP. So L is given to you, and solve the equation. Solve the equations means solve the equation P minus D. P is equal to dq of L of XP. So that L of P. That's why L of Q. That's what you have to solve it. So define HP like that. Then H is continuous, convex, and cohesive. So L and H behaves in the same way. That's what it shows, that H is H is cohesive. So that means that one H satisfies the continuity, convexity, and cohesivity. You can also define H star now. Therefore, therefore H star exists, right? Because it satisfies the similar property. You take the supremum, so H star exists, and this you already know, H is equal to L star, that you know already, and H star is L. So you will get back your L. So L is defined, you get H is equal to L star, which you already proved it. But I am saying that H also satisfies the similar properties of continuity, convexity, and cohesivity, and hence you get H star, you can define, and that H star will be L. So let me try to finish before the lecture, even though it's delayed a little bit. So let me give a quick proof of that before ending this lecture. Okay, and convexity is easy to check, so I will not do here. Convexity, easy to check. So that is your exercise. Okay, and then what you have to prove is that you want to prove claim. Maybe I will prove one side. You want to prove that H star is equal to L. This is what you want to prove it. The all other things are proved. Okay. So cohesivity also you can prove everything. So before that, let me see the cohesivity. So first let me do the cohesivity, so which I will prove it here. So take lambda equal to positive. take lambda greater than 0, then by definition, because H is supremum, okay, H is the supremum of that one, take Q is equal to lambda P, H star is supremum, P mod P implies your HP is greater than or equal to P into lambda P. So I am taking P into lambda P because H is the maximizer. So for any choice of this one, it will be smaller. L of lambda P by mod P. Okay. Look at this vector. This vector is belongs to on the ball of radius lambda. If you look at it, this is the ball of radius lambda. That means it is on a compact set. So therefore, this has a maximum. This has a maximum. You see? So you check these proofs. Because it's a L varies over a boundary of a fixed ball, this has a maximum. Yeah. That means once you have a maximum n, since this is a minus sign, I will have mod P, lambda into P is mod P square. So you have lambda into mod P minus some fixed constant here. Okay, because it's on the boundary of the ball. That implies HP by mod P is greater than or equal to lambda, okay, minus m. So you can see that when you take, this is mod P, so you divide minus m by mod P. So if you want to take it, okay, m is the supremum of that one. So okay, so so what is there? There's something. M is the supremum. Okay, yeah. Now you, if you take as mod T tends to infinity, as mod P tends to infinity, fixing lambda implies the limit may not exist, but I can call it limit infimum mod P tends to infinity is greater than or equal to lambda. See, now lambda is arbitrary. These are all some analysis technique. Now lambda is arbitrary. Lambda is arbitrary. Take lambda tends to infinity now. Now m is not there, so I can take lambda tends to infinity. That implies this is HP by mod P. You get that the limit exists and the limit HP by mod P. Limit exists as an infinite quantity. Mod P tends to infinity. The limit inf goes to infinity. This will become infinity. So it is quiescent. Okay, so you have to prove now the main claim that one H star is equal to L. So since I don't know, it may take some time, so maybe I will skip the proof because proof, refer the book. So proof, it's not difficult. Refer the book. AKN plus PST. So yeah, that will take another 5 to 6 minutes. Probably I'll skip the proof because it's already 35 minutes. So please go and have a look at the proof. So as I said, that's why we will not be able to give all the proofs, because if you want to give all the proofs, and even if you want to give a basic introduction to Hamiltonian, it takes maybe 10 hours, but or at least 5-6 hours. But what we have covered here is only some 3 hours or something like that in 6 lectures. So I will stop here, and now with this material we are going to basically state, we are not going to prove anything in the last lecture on Hamilton-Jacobi equations. We will be stating the existence and uniqueness, as I said, in a weak sense. Thank you. Thank you very much.